Alright, this is the notes for section 6.9, complex numbers. And if you remember back in 6.8, we looked at an imaginary number, and that's kind of was our start at looking at complex numbers. And we defined an imaginary number as being the square root of -1 is going to be equal to I. Now, what we're saying with complex numbers is that every number, real number, imaginary, or a combination of both, can actually be written in this form, a plus bi. Okay, and that's what we're going to look at today, and kind of how complex numbers operate, etc. So let's begin with the definition of complex numbers. A complex number is a number of the form a plus bi. Notice how we have a first and then bi second. A and b are real, so these are real numbers, a and b. And I is that imaginary number, which is the square root of -1. We say a is the real part and b is the imaginary part. For example, 4 plus 3i, we would say that 4 is the real part and 3 is the imaginary part, not 3i. Okay? For complex numbers to be equal, both the real and the imaginary parts must be equal to each other. So as we think about complex numbers, we have to think about them kind of like we would with our real numbers, in that they're going to have properties just like real numbers. So here are the properties that we have for complex numbers. The complex number postulate tells us this, and that is, first of all, the addition and multiplication are commutative and associative, just like real numbers. Okay? Multiplication is distributive over addition and subtraction, so we can use that distributive property that we've used quite a bit with just real numbers. Now, just like real numbers, there is an additive identity and a multiplicative identity. The additive identity is 0 plus 0i. In other words, if I take any complex number and I add 0 plus 0i to it, I'm going to get the exact same thing back. And we have also a multiplicative identity, which just says, hey, if I have any number and I multiply it by 1 plus 0i, I'm going to get the same number back. Okay? Every complex number, a plus bi, has an additive inverse, and that is, if I add it to a plus bi, I get 0. So a plus bi and negative a minus bi, or plus a negative bi. And the multiplicative inverse is the same thing. We have a multiplicative inverse that says that, hey, if I take and multiply by 1 plus a plus 1 over a plus bi, it has itself undoes itself and gives us the value of 1. Now, this is all provided that a plus bi is not equal to 0. Okay? And then finally, the last property here, the addition and multiplication properties of equality hold. So if you think about what we've done with addition and multiplication properties throughout your learning about real numbers, those hold for complex numbers as well. Alright, so let's apply some of these properties to do a couple of problems here, some example problems. So the first one, it says write 7i times the quantity 9 minus 6i in a plus bi form. So we've got an imaginary number times a complex number, and we want to get our answer in that a plus bi form. Well, here's how we would go about doing that. Because the distributive property works, I'm going to take 7i and I'm going to distribute it across the parentheses here. So I have 63i minus 42. Now I have I times I, which is I squared. Well, I squared is going to be equal to -1. And -1 times 42 is just a -42. Well, if I have -42, that in essence makes this whole thing a positive 42. So now the last thing I have to do is I have to put it in the right form. The real part goes first, the imaginary part goes second. So I'm going to put the 42 first, and then the 63i is going to be added on at the end. Alright, let's look at number 2 here then. And in example 2, we want to multiply these two complex numbers together. So this is our first look at just taking two complex numbers, and how do we do that? How do we multiply them together? Well, we're going to multiply them together just like we would, almost as if I were a variable, and we're going to use our FOIL method to do that. So I'm going to take first outer inner, and last to get my answer. So if I take my firsts, I get 30. My outers, I get negative 10i. My inners, I get positive 42i. And then finally, my last term, 7i times negative 2i, gives me a negative 14i squared. Now, anytime you get that I squared, we have to remember that that's equal to negative 1. And negative 1 times 14 is like a negative 14. So this becomes a positive 14. So I have 30, and then plus, this becomes a positive 14. 30 plus 14, which gives me 44. That's the real part. And then the imaginary part would be the combination of these two middle terms, which comes out to be 32i. So my answer here is 44 plus 32i. All right, so in order to add, we're just adding the real parts together, and we're adding the imaginary parts together, and same thing would apply with subtraction except for subtracting. And multiplying, we know that we can use that distributive property. We can use the FOIL method to help us do that. The one thing that we don't have yet is the ability to divide. So in order to do that, we have to know a little bit about complex conjugates. And complex conjugate is the following. It says that a plus bi and a minus bi are complex conjugates of each other. What that means is if I multiply those two together, I will always get a real number. Okay? Complex conjugates are useful when dividing complex numbers. So in other words, if you think about it, a plus bi, and I multiply it by a minus bi, and if I use my FOIL method, I get a squared minus abi for this part here, plus abi for this part here. And then finally, this last one would be minus bi squared. Well, if I take these middle two terms and combine them, one's positive and one's negative, so they actually just cancel out. And then an I squared makes this whole thing, negative b I squared would be the same as plus b. So I'm sorry, this should be b squared I squared. So it'd be a squared plus b squared, because remember I squared is equal to negative 1. So really, using our complex conjugate, if we multiply them together, we will always get a squared b squared. So let's take a look at example 3 here. We have a complex number 5 minus 2i divided by another complex number 3 plus 4i. Well, in order for us to do this division, in order for us to get it in a plus bi form, I really can't have any imaginaries on the bottom. So the way that I can take care of that is by using the complex conjugate. So in other words, anytime you have division, you're going to have to use that conjugate. And what you do is the following. You multiply top and bottom. Sorry about that. You multiply top and bottom by the conjugate. So I'm going to multiply both the top and bottom by 3 minus 4i, because it's the conjugate of what's on the bottom, 3 plus 4i. Now, when I multiply that bottom, remember I said it was going to be a squared plus b squared. In other words, 3 squared plus 4 squared, which is 9 plus 16, which gives me 25. Well, I'm just showing how I'm getting that right here. If I use my FOIL method when I multiply these out, I get this, which simplifies down to 25. Well, on top, I'm going to also have to use my FOIL method. So I'm multiplying using the FOIL method up there. And first, outer, inner, and last. Now remember that this can become negative 8. So this right here is really negative 8. And that really is part of my real part. So when I put the negative 8 and the 15 together, that's where the 7 comes from. And then I've got a negative 20i and a negative 6i. That gives me my negative 26i. And then finally, I need to write it as in a plus bi form, so I need to split that up. So remember that I have to put 25 under both of these values from the top, so it'd be 7 over 25 plus 26 over 25 times I. So I've got my a part, my b part times I. All right, so given what we've looked at with complex numbers, where does that thing, where do complex numbers fit in our whole number scheme? So up until now, our number system looked like this right here. We didn't have this whole right wing of the number system, but really complex numbers are now at the top of the number system because every real number can be written as a complex number. It's just that b is 0. Every non-real number obviously would be complex, so that would be anything in the form a plus bi. And then of the non-real numbers, we have some that are pure imaginary numbers, which just would have just the a value would be equal to 0. All right, the last thing I have on your notes here is a problem involving an application with electrical circuits. And if you're given this, z sub t is equal to z sub 1 times z sub 2 divided by z sub 1 plus z sub 2, what I'm going to have you do is see if you can do this example problem, and then we'll talk about that in class tomorrow.